All right, welcome everyone. I see we've got a few folks joining us still, probably coming from the previous session. So welcome. I'm glad that you are here. We are here for the track 2, the Public Health 2 session for UC GIS week. We've got some really good talks lined up. I was just chatting with our speakers and I'm really excited to hear from them. And I think we should just go ahead and get going. But first, you've probably seen this slide or something similar as you've been in other UCGIS week sessions. Just want to remind you that we've got more going on our Slack channel, our Slack workspace, ucgis.slack.com, so you can join us there. We're in track 2, so you can join the discussion on the track 2 channel as we go, but also you can use the chat function in Zoom as well. Let's see, is there anything else you need to know? So we're going to ask you to put your questions for our speakers in the chat window in Zoom, and our helpers and the folks staffing the conference will ask those questions to our speakers just to keep background noise down and stuff like that. But otherwise, I think, oh, one more thing I should remind you of, we have a survey, so we'll put the links in Slack and we'll email it to you, but you can also zap the barcode on the screen if you want to fill that out on your phone. So with that, I'm going to stop my screen share, and I think what we will do is we'll just jump right into Taylor's talk about interactive data-informed fertilizer applications for California farmers. And this is so cool. So take it away, Taylor.
Sorry, Zoom, PowerPoint went over Zoom, so. Okay. Everyone can see that? Good. Okay, so I am Taylor Nelsen, and I am an assistant specialist working in grain cropping systems at UCDavis. I put my email up there if there are follow-up questions after the presentation and anyone wants to contact me. And like Michelle said, I'm going to talk about interactive data-informed fertilizer applications for California farmers. And I'll leave a few minutes at the end for questions if anyone has any. Okay. So first off, I want to start by saying that this is just one piece of a much larger project with field sites and collaborators throughout the state. We've been funded by a wide variety of entities, not only to build the interactive tool that I'll be talking about today, but also to demonstrate the practices in farmers' fields that they use in the management tool that I will be talking about. So people from UCDavis, people from Cooperative Extension, as well as a bunch of growers throughout the state have helped with this. So usually I'm talking about fertilizer applications and this project to farmers and to advisors who are familiar with the field concepts, but not necessarily the technical concepts of GIS or our web application. But I'm assuming this audience doesn't necessarily know much about fertilizer applications or grain production in California. So I'm going to start with some project background to give everyone some context for this work, but I hope to focus on how we really developed our interactive website that provides farmers with nitrogen fertilizer recommendations, and then walk through the website itself to show its capabilities. If we have time, I'll touch on how we are working to educate farmers and advisors who we hope will be using this tool starting this growing season. So with that, when most people think of California agriculture, they don't think of wheat. They probably think of almonds or wine or one of the more high value crops. But wheat and other small grains such as barley are grown throughout the state, as you can see on the map. And often these grains are used as a rotation crop, so they're planted between seasons of other high value crops such as vegetables. And often this means that farmers aren't paying as much attention to their wheat crops as they are with other crops. Then this leaves a lot of room for potential management improvements, especially fertilizer improvements, which our project is focusing on. So most of the wheat in California is planted in the fall around this time of year, and it's grown in interaction with winter rainfall. And this makes management vary from year to year, as well as from place to place. They're just adding another layer of difficulty for these farmers. So as you can see on the maps shown, there's a huge variability in precipitation between a dry year on the left, like the 2013-14 season, it's a pointer here, and a wet year like the 2016-17 season. And as well as the year-to-year variability, average rainfalls vary from like 2 inches down in the Southern Valley, Imperial Valley in Southern California. And then there's places up here in the Sacramento Valley that have more than 24 inches on average per year. And we only expect these extremes to be more exaggerated as time goes on as a result of climate change. So what does this have to do with fertilizer, namely nitrogen fertilizer, which we're hoping to improve the management of? So, I'm going back, there we go. So nitrogen is essential to pretty much all life, and it's often the most limiting element for crop growth. So this means that the quantity and timing of nitrogen fertilizer applications are among the most important things for not only the productivity, but also the profit of a wheat crop, as well as environmental impact. So for most commercial farming operations who are growing wheat on a large scale, nitrogen fertilizer is pretty inexpensive compared to the potential loss of not applying a nitrogen fertilizer. So what often happens is that farmers apply nitrogen fertilizer in excess of what the crop can use. And this ensures that the crop has enough nitrogen to reach its full economic potential, but the overuse or mistiming of when the nitrogen fertilizer apply often results in many negative environmental externalities. And as a result, has really been started to be regulated throughout the state. So what do I mean by the negative externalities and when do they happen? Most of them happen because nitrogen moves with water and it moves through the soil and into the plants through mass flow. But if plants do not need the nitrogen in the soil, it can run off into waterways, leading to things like algae blooms. It can leach into groundwater, contaminating drinking water, things like that. And unfortunately, it's common practice to apply nitrogen fertilizer before or at the time the crop is planted. So at the very start of this graph. It's often logistically easier for the farmer since they're already in their field and it's often drier at the beginning of the season. But as you can see in the first few months that plants are in the ground, there's not a lot of nitrogen use. And between October and the end of January, there's actually only about 10% of nitrogen for the entire season used. But often there's been over half the seasonal rainfall at the same time, as you can see. So during this time, the nitrogen is not being used by the plants, it's often being lost to the environment. So not only is this bad news for the environment, we have also found that it's not best for crop outcomes, even though the plants look better in picture A here. They were given all their fertilizer at the beginning of the season, and the plants in B were given the same amount of fertilizer just after this picture was taken. And they ended up having higher yields and higher protein, and so having more economic return for the farmers. So taking these dynamics of wheat growth and fertilizer use in the California environment into consideration, our interactive tool works to answer the question for each specific field in a given year with all the variability between them of when should a farmer apply nitrogen fertilizer and how much fertilizer should they apply in order to maximize their crop outcomes while not over applying and losing money on that fertilizer, as well as losing nitrogen to the environment. So how do we build this tool? The first step in building our interactive tool was a lot of behind the scenes work that I'm not going to really talk about, but wanted to mention. We took a lot of field measurements on how fast crops were growing, how much nitrogen was present in the soil, and the response of different crops to different amounts of nitrogen fertilizer. We referenced a lot of data and models for other groups, and we developed empirical models from the data we took of plant nitrogen uptake and plant yield increases from nitrogen fertilizer applications, many of which are in the process of being published. And then in order to scale these models and our measurements from single fields where we had these experiments to any wheat field in California, we needed larger data sets of weather and soil properties. So we tested several sources of data, but ended up using daily prism data, which is weather data available for the whole country on a 4-kilometer grid that is results from an incorporation of monitoring networks, as well as like satellites, as well as on the ground weather stations. And they do quality control measures and model the weather output on a daily basis. So we use that data source. We also use relevant soil properties as a weighted average from the top foot from the Cerys database. And if you're interested in how we did that, we have that on our GitHub as part of another tool that we created. So with these many sources of data, as well as the large amounts of it, we still couldn't scale to any field on any given year, just using spreadsheets. We needed a database. And as agricultural researchers, databases aren't really our specialty, but with the help of the UCDavis's library, their pilot database management service, and research support engineers there, we built a workflow and Postgres database. So we still collect data in the field and we store it in spreadsheets or just regular CSVs, and we keep those. But we also use this Postgres data management app to insert, update, and manage most of the data we collect. And we also have automated downloads set up for the data that is updated on a daily basis, such as the weather data that goes into our Postgres database. So this allows us to have a large amount of data, make it quickly available in an automated and reproducible way to use on our online app, as well as internally for our continued research. So like I mentioned, we are not database experts, but we need the power of a database. So if you're interested in this application that we use, here's the GitHub link for it as well. It was developed in collaboration with the UCDavis library, and it gives us the power of the Postgres database, but we really only interact with our database through this application or through R for our analysis and our web tools, because that's what we are comfortable and kind of use on a daily basis. And again, we've really tried to make a lot of this work open source as much as possible. And I'm kind of giving a high level overview, but if you are interested in database design, our design and several other labs designs that have used this are up on GitHub as well. So once we had our database in place, it enabled us to start building interactive tools that utilize the data and the models that we developed. It allowed us to take old and new information, and instead of writing it up as text or in a table and making generalizations about the whole state or large regions, we are able to start making recommendations for each field. And so more specific data is especially important in this case of fertilizer management for the California wheat, but interactive tools in general have also been found to do a better job at engaging users and communicating data and concepts. Users learn as they're doing how the different pieces fit together and what it means for their individual situation. That's kind of the goal that we had when developing these interactive tools. So our tool is called the Nitrogen Fertilizer Management Tool for California Wheat. And it does a couple of things. It gives users context for the variability of that season. So what does precipitation and plant growth look like in their field for this season compared to past seasons? It integrates all of our site-specific data and models, as well as information the user supplies about their management and measurements they take in the field. And then finally, it provides a nitrogen fertilizer recommendation and predicted outcomes for different nitrogen fertilizer applications. So we built this tool using RShiny, which is a platform used for making and building interactive apps. It is fully customizable to kind of different things you want to do. And it has a very robust knowledge base. So there are free tutorials online, as well as forums where you can ask questions about troubleshooting, but highly recommend. It's open source, so free to use, and it's based in our programming language. So a little bit about RShiny, so you know what's happening in this interactive app. So an R Shiny app runs R functions and scripts, but it allows the user to make changes. It has a few basic parts, pretty much the inputs, processes, and then finally the outputs. And the inputs are pieces of information collected from the user. The processes all happen in pretty much an R server. So they're just R pieces of code, and then outputs are the results of those processes and the things you want the user to see at the end. So for our application, we have inputs of a location of interest, a time period of interest, and then the field specific management decisions and measurements. Then we have outputs of the seasonal context, like I said, certain weather data throughout the season. We estimate the growth stage of the plants. We give soil nitrogen fertilizer equivalents. And finally, pretty much all of this leads to a nitrogen fertilizer recommendation. In a diagram, just so it's kind of in a visual way, this is what it looks like. Like I said, these are the inputs or the main inputs: location, time, specific management decisions. And through these processes in the middle, like using the PRISM data and the growth models, we can give users a seasonal context, use our nitrogen response models, and recommend them a nitrogen fertilizer rate. So in the last few minutes, I'm going to walk through the app and use a specific field that we have actually tested it on this past season. And you're welcome to explore this after the presentation as well. So let me just switch over to that. And here we go. Okay, so there's an about page. If you want to know more, if there's questions or feedback, we have a form for people to fill out. So I'm just going to jump right in. And this is a GIS conference. So the very first thing we have here is an interactive map. And so this is where a user could select what their place of interest. So they can drag and drop their pin, and they can also just enter in an address or a set of coordinates. So I'm going to enter in the coordinates for a field that we worked with. And as you can see, you can switch to satellite data. And here's the field that we had last season. Then you want to select a period of interest. We usually ask people to select their planting date. So this one was planted December 11th of last year. And then usually what happens is during the season, they're saying when they're making a decision about nitrogen fertilizer, then this is the date that we would want them to enter. So if it was this season, it would be this date, and we actually have forecast data for the current season. They can choose a crop variety if they know it, and if any irrigation or if their field had moisture in it when they were planting, so that we know when the seeds germinated. So those pieces of information are used to then access the database and gather up all the weather data and use the models to then predict a growth stage of the plants. It also gives people a graph of what the current nitrogen uptake for the season, the current precipitation, and they can compare it to those 10-year averages if they wish. And if you had irrigation data, you could see it in this graph on seasonal water. It loads. And you can also download your data here to see all the precipitation and nitrogen uptake data that we're using. So the next step in this is supposed to be, I'm going to restart it. That accesses our data. And then the next step is to actually access and add the in-field measurements that the growers take. So they are going to take kind of their measurements of how green the field is and soil tests for the field. Let's see. I have a backup if it's not working. So 1 second. There we go. So the next page looks like this, and it asks what are the site-specific measurements that a farmer has taken, and it only works with good measurements from a field for that. And then it says, when were the measurements taken? When is the fertilizer going to be applied? We ask how green the plants are and what kind of soil nitrate measurements there are. There's little calculators to help them calculate what kind of fertilizer, what kind of sufficiency index, which is how green the plants are. And then there is other tools as well of looking at just the soil nitrate or just the weather data and how to actually do those tests, which is free to explore if anyone wants to explore that data. So then finally, we asked them, what is the typical yield and protein? Has there been any other nitrogen fertilizer applications on the field before this one in season? And then we give a recommendation of, here's our recommendation, here's how much yield increase is expected, as well as protein increase, and then show that even if you change it, you're not going to necessarily get more yield for increasing your nitrogen fertilizer recommendation. So with that, I'd say there's a lot of more information on our website here about the project, about the interactive tools, and we actually have YouTube videos on all of them and how to use them. So we have this main one on nitrogen fertilizer management, but there are other ones that are more specific to just weather data in California, just soil data in California, as well as other grain related things. So there are any questions in the last few seconds?
So we do have a couple of minutes for questions for Taylor. So feel free to put your questions in the chat window, and Carlos and I can field those to Taylor. So I'll give you, I know it takes a second to type. So if you have questions, go ahead and type them in there.
I'm guessing everyone tried to access the application at once, and that's why it crashed.
And that's okay. That's how it goes. So you try to present something live and it of course wants to give you a headache. But that was great, Taylor. I have a question for you. I'm wondering like what kind of planning goes into this? Like obviously it didn't all just happen. So like, did you build this in stages, or was there like a list of features you wanted to add? Can you talk a little bit about the process of building these kinds of tools?
Yeah, so we started off with a rough sketch of kind of what we wanted. We already had a good understanding of the dynamics of nitrogen fertilizer and what kind of things were needed for wheat management. So we knew that weather was going to be an important feature. We knew that taking measurements in a field of how green the plants are and what kind of nitrogen is already in the soil was very informative. So we kind of just started with that and say, these are the pieces we want. It was kind of step by step. When we realized we needed a database, we had to sketch out that whole database and figure out how to add the data, how to get the data we needed, and then how to integrate it into our app. It has been about a 2-year process to get to this point of just building the database and the application. We already had a lot of the data and models before that.
Well, thanks for answering that. We've got another question in the chat, but I think given the time, we need to move on to Yanjia's talk. So let's go ahead and switch over, and maybe Taylor can take a look at that question in the chat and type up an answer there. Next up, we have Yanjia Cao from UCSD, who is going to be talking to us about modeling dynamic change of marijuana use disorder in California.
Okay. All right. Thanks, Michelle, for the introduction. So yes, I'm a postdoc from UC San Diego School of Public Health, but I'm basically a geographer for my PhD, master, bachelor. So basically a health geographer to talk about the changing dynamic of marijuana use disorder in California. So this research is about marijuana use disorder. As many of us know, recreational marijuana has been legalized in many states in the whole country, especially in blue states. And California legalized the recreational marijuana in 2016. And it actually raises some public health concerns in the past few years because of use disorder. Some patients might be sent to hospital or ER, emergency medical service for treatment. So many previous research have looked at the state level pattern about the marijuana use disorder, but sub-state level research is still lacking. So why do we care about sub-state level pattern? Because there are a couple of reasons. One is we want to know the regional variation. It's not only about one whole state, or it's decreasing or increasing, but within the state, there are many variations, like between counties or between townships. And it also helps the policymakers, especially the local policymakers, to target the high-risk regions so they can adjust their marijuana intervention strategies or to relocate their marijuana treatment services. And also we can explore some local factors, especially neighborhood characteristics that is associated with the marijuana use disorder. So the major question for this talk is what is the spatial and temporal pattern of ED and hospital discharge involving marijuana use disorder during the past 10 years. So this is a lightning talk. I only have 10 minutes, so I'm not going to cover everything in this study, just a very brief overview of the spatial temporal pattern. So the data source we used in this research are from the California OSHPD. It's annual data from 2010 and 2019. We used the ICD codes to retrieve the marijuana use, marijuana dependence or use disorder. Basically, they are diagnosis codes from the doctors or from the patients. So ICD-9 code, it covers 2010 to 2015 and from 2015 to 2019, they switched the code to ICD-10. So that's some difference. And the resolution is zip code. That's the best resolution we can get from this data set. And we convert it to SIGTA so we can do our analysis with the census data. And this is a very brief overview of the data set. In general, the statewide, you can see the emergency discharge have a higher rate. This is a rate by 100,000 population within the SIGTA. There's higher rate in emergency discharge, and there's higher rate for male and higher rate among the Hispanic, non-Hispanic Black population. So that's an overview of our data set. So in this research, we applied this time series clustering. This approach is a data mining approach. It looks at the trend over time for each SIGTA. So basically the idea is SIGTAs with similar trend over time will be grouped into one cluster. It's not a spatial cluster, it's data cluster. So the approach has many different distance measures. It could be Euclidean distance, which measure just the quantity-based distance. But in this case, we want to know the changing pattern. So we use this shape-based distance. And we used our R package, DTW class and TS class. And just to save some time, I just briefly introduce, we use cross-validation in this research to determine the number of clusters. There are a bunch of indices in this cross-validation, and we picked 4 clusters for both ED discharge and also hospitalization discharge. So this ED discharge results, we can see these 2 figures, actually the colors corresponded to each other. Cluster 1 and cluster 2, they basically decreased since 2016. And cluster 3 actually increased very sharply, and cluster 4 kind of become flat in the recent years. And if you look at Los Angeles, it's basically becoming stable. And if you look at this increasing one, it's mostly in the Santa Barbara County here. And also Sacramento, I think it's Sacramento here. And actually this cluster 3 only comprised about 8% of the population in the whole state. So most of the state actually decreased in the recent years. And hospitalization presents a similar pattern. Most part of the state declined since 2016, and only one cluster, that is cluster 3, they actually increased in the past 3 years, and they are mostly in the Central California here. So yes, what else in this paper? I'm finishing this talk. We also look at the changing pattern in each demographic group, and also the social demographic characteristics that are associated with each cluster. So in those increasing sectors, what social demographic characteristics are associated. So we have our incoming paper is still under review in drug and alcohol dependence. And I want to thank our collaborators, my PI in UCSD, Nguyen, collaborators Marta and Jay, they are from Beckman Research Institute. They are extremely helpful for this project. So I really appreciate that. And this is my personal contact information. If you have any question, you can reach out to me, and that's my personal website. And feel free to contact me if you want any suggestion, help on geospatial method. Thank you.
Thanks for this talk. This was super interesting. We do have a question for you in the chat. Oh, another one just came in, but Carlos is wondering if there is, if you can discuss why it looks like cluster 3 is increased. And he says, I thought it is kind of interesting to see Humboldt in that cluster. So I guess just a little bit more discussion about what you see with cluster 3 in your results.
Are you saying hospitalization or?
Oh, that's a good question. Which?
Well,
Yeah.
Maybe we can start with anyone. Maybe emergency discharge, that's cluster 3. So yes, around Sacramento and Santa Barbara, that's increasing. And hospitalization, it's basically in Central California. We actually did a local GIS org, but just to describe the pattern, but not really showing here. I'm just describing the pattern. Maybe you can have a close look at the map.
I was just wondering, like, cluster 3 is clearly the outlier here. Was there a narrative of why you think that that's different from all the others?
I don't think there's a why question answer. We did look at the social demographic variables, but we don't really pick any special reason why there's increasing. Yeah, that's a good question. We probably want to look into that, but not quite sure about why. I can tell you about the why for the decrease based on previous literature is most after the legalization, actually it's more socially acceptable. So it's actually becoming less likely to get overdosed. So that's some reason for the decreasing, but for the increasing part, there are some socioeconomic factors we looked into, and there's some difference in those areas. That's what I'm getting at this moment.
Thanks for that. That's a really interesting thought about like how laws can affect whether people are overdosing on something or not. I think that's an important thing to keep in mind. So there are a couple more questions in the chat, but given the time, maybe Yanjia, you can take a look at the chat and answer
Yeah, sure.
there. But I think next we're going to move on to Cerys Edwards from UCLA, who's going to be talking about inequalities in the distribution of mental health facilities.
Awesome, thank you. There are some gardeners outside and they're being pretty loud. So if you guys can't hear me, just feel free to interrupt and let me know. But
You sound clear here.
okay, good. Okay, so my name is Cerys Edwards. I'm a third-year undergrad at UCLA, majoring in geography. And I'm currently working as a cartographic materials student assistant with the Henry J. Bruman map collection at UCLA's Young Research Library. And today I'm going to talk about my research project that looks at the distribution of mental health facilities in Santa Clara and Los Angeles counties, with the goal of looking at regional inequalities. So this project was originally designed for a geography student research program 99 one-unit course that I completed last spring under the guidance of Dr. Sierra Burkhart. And my original goal for that spring quarter was to look at the distribution of mental health facilities in Santa Clara County and compare that with the distribution of various socioeconomic factors like race and income. And then I hope that this research would be able to inform the placement of new facilities or inform strategies to expand telehealth. And then this quarter, I recently added to my research by studying the mental health facility distribution in Los Angeles. And my methods, I used ArcMap to conduct my spatial analysis and create maps. I used R to organize my data and look at the correlations between variables. And I used GIS to conduct a hotspot analysis of the distribution of mental health facilities. So to go over the literature a little bit, the literature on healthcare distribution inequalities show that nationwide higher income neighborhoods have greater access to healthcare professionals and community resources. But in Ohio, there was a study carried out that showed that low-income neighborhoods had a perception that their healthcare was actually worse than it ended up being. These are my points that I used for my study of Santa Clara County. There are 76 of them, which is definitely not all encompassing, but I got my data from the California Health and Human Services Agency. And so that's just what they included. Those are all of the facilities that are certified under that agency. And so this map shows the results of a hotspot analysis of per capita access to mental health facilities organized by town in Santa Clara County. So when I first looked at this, I kind of thought like there's a high clustering of facilities in like Campbell, Los Gatos, Saratoga area. And in my mind, those were kind of like more like higher income areas. So I thought that might be something, but also Palo Alto kind of has that reputation in my mind. And that wasn't really backed up with quantitative data. And then to move on to my study of Los Angeles, the data was obtained by the City of Los Angeles GeoHub, and it has 916 points. So studying LA was a lot easier because the data is a lot more readily available, and the LA County Department of Mental Health has their own like geospatial initiative. So a lot of the data is readily available. For example, they have this map that I found on the Department of Mental Health webpage of just like client density, and they use a network analysis to show mental health facility patient density in the county. So this map shows my hotspot analysis of a variable I called facilities proximity. So using a tool I created in Python for one of my GIS classes, I calculated the percent of each region that is within 1 mile of a mental health facility. And so you can see there's a pretty big high cluster in the center of LA there, which kind of follows because that area is just more dense in general. So it would make sense that it would have a greater density of mental health facilities. And then I put this into a graph in R, comparing it with median income. So at the bottom we have median income, and on the y-axis we have the proportion of each census tract, which is within 1 mile of a mental health facility. And there is technically a correlation, right? But you know, it's not super clear from first glance. And it is a negative correlation, which goes against my hypothesis and the literature. But yeah, it's not really super clear. And then another way of looking at access to mental health facilities would be to measure the number of mental health facilities per capita in each region. And so in this map, the clusters are smaller, but they are there, and they are statistically significant. And then, yeah, so there is clear clustering, and it is definitely significant. But the correlation between that clustering and variables like income is not super clear. I also noticed that some areas near college campuses were in the low cluster area, which I just found kind of interesting, and I was wondering why that is. So it's something I'm going to be looking into more. And this project is still very young. It's still in its early stages. This was, you know, my first experience really with doing like college research outside of a class. So there's definitely a lot of steps to take to make this project more complete. For example, for Santa Clara County, creating a more complete list of facilities. There's only 76 points in the shapefile I was able to form. So it would definitely be helpful to, you know, find more to add. And then also considering the capacity of these facilities, because the way I measured it was just by a count of facilities. But, you know, some facilities can take more patients than others. And so that's something that's really important to consider. But yeah, I have to find that information somewhere. And then learning how to conduct a network analysis so that I can analyze travel time to mental health facilities rather than just as the crow flies distance. And then maybe collaborating with the LA County Department of Mental Health. They have a really cool geospatial initiative. And yeah, that would be cool. And it would make my results, you know, more precise. So thank you all for listening to my presentation. I put my email there if you have any questions or any suggestions on, you know, how to understand or add to my results. I'm totally open to that. Thank you.
Great, thank you so much for your presentation. We've got one quick question in the chat. So Leo wants to know, what is the definition of high and low density, and why did you choose chloropleth map instead of a heat map to visualize density? So questions about cartography.
Yeah, so the high and low, if you've ever used Geoda, you can sort of put in there your data, and then it sort of tells you where there are particularly high clusters of like where where values are particularly high compared to the rest of the values and where they're particularly low. And then why did I choose choropleth map? Just simplicity purposes. You know, that's kind of what I'm used to, and it's more simple.
Great, thanks for answering those. Just want to shout out to UCLA Geography. I'm an alum from that program myself, so yay UCLA, even though I work at Davis. So next up, thank you again, Cerys. Next up we have Andrew Nguyen and Yao Fu from UCSD, and they're going to be telling us about their talk, GIS and Community Homelessness Solutions, creating mobile apps for outreach and environmental monitoring, something very much needed in this day and age. So take it away, Andrew and Yao.
Thanks so much, Michelle. Yeah, I'll just share my screen really quickly. My name is Andrew, and I'm a research associate with H-Hub, the homelessness hub at UC San Diego. And joining me is Yao Fu.
Hi, my name is Yao. I'm a fourth-year undergraduate in urban studies and planning at UC San Diego, and I'm also a research assistant at H-Hub.
Yeah, so a quick background on H-Hub. It is an open data repository looking to centralize collaboration, data sets, and research around homelessness in the San Diego County area. And so this presentation will be on our recent work on 2 different projects in the realms of creating data collection instruments specifically for homelessness outreach and environmental monitoring related studies. So as mentioned before, H-Hub is a open data repository, and we're teaming up with a few entities that are listed here. The San Diego River Park Foundation, which is a nonprofit organization that is tasked with the environmental conservation needs of the San Diego River. That includes mostly trash and environmental biodiversity upkeep and maintenance. Then we are also joined by the People Assisting the Homeless, or PATH San Diego, which is a partnership of several entities that are working in the sphere of homelessness solutions, be it outreach services, rehousing folks. And then lastly, the Southern California Coastal Water Research Project, which is a research body that is engaged in the evaluation and maintenance of waterway qualities, specifically in this case, the San Diego River. So our first project occurred in late 2020, or started development in late 2020, when the San Diego River Park Foundation and PATH collaborated with us to turn one of their paper surveys into a digital instrument. This instrument would be to keep track of any individuals who are unhoused in the San Diego River who requested any resources or outreach with the PATH individuals that were going along with these quote unquote river walks with the San Diego River Park Foundation. They were interested in understanding the spatial distribution of their outreach and resource needs. And so we created an instrument on the Survey 123 platform, which is included in Esri's ArcGIS platform. We then created dashboards within HEOL, and our partners at PATH and San Diego River Park Foundation were given community logins to access the data, the applications, and the dashboards. So obviously, for privacy reasons, we cannot share the actual data that were collected during this study and still are collected, but this is a quick demo of what the mobile application looks like. It is form-centric. Survey 123 allows all different types of display and skip logic, making it a very robust and useful tool in the field where many different types of questions need to be posed to individuals.
So moving on to SWRAP and wastewater monitoring. As previously mentioned, SWRAP is the Southern California Coastal Water Research Project. SWRAP was formed to conduct an analysis of wastewater in the San Diego River. This wastewater mainly consists of water that has been contaminated with anthropogenic fecal pollutants. Importantly, one of the goals of this project is to understand the wastewater impacts from the unhoused community living in and around the San Diego River. Thus, this project is a partnership with the outreach and service provider PATH. Additionally, a partnership with the San Diego River Park Foundation was formed to leverage past environmental monitoring data. A survey instrument was built by HUB in late October of this year to aid in the data collection process. This survey instrument was built again in Survey 123 and field maps, which enables a survey instrument to incorporate aerial viewing and editing of input data. The survey instrument created for SWRAP is not lengthy or complex by any means. However, the spatially enabled platform provided by Survey 123 and field maps allows for greater precision and accuracy in the collection of data that would otherwise not be feasible. Finally, SWRAP's partnership with PATH allows PATH to provide outreach for any community members located within the flood-prone areas based on data from the San Diego River Park Foundation and HUB.
And here we see samples from the survey instrument developed for SWRAP. And you can see that this is now a more map-centric application enabled by field maps, but it is a Survey 123 form that is brought in as a feature layer into field maps. So it has all the same skip logic and display logic, just in a map-centric format, which is really important when field workers need to know their spatial relationship to existing features if they wanted to visit the features again for editing or to collect more information at that point. And here we see the data visualization and dashboards that are enabled by the ArcGIS online environment, the overall statistics, and then the map viewer and tabular data viewer. This is what our stakeholders and partners get to see on their end, and they are given access to downloading the data and analyzing it themselves.
So with regards to further application and lessons learned, the importance and feasibility of centralizing data collection within a spatially enabled clearinghouse cannot be overlooked. This is where HUB steps in. HUB brings together disparate data from several different sources and provides standardized access and maintenance of the data and instruments. Due to the interdisciplinary nature of this project, cross-collaboration is key to addressing multi-level issues like homelessness and environmental conservation. Most paramount is privacy. This is especially true in a project like SWRAP that may collect personal or sensitive data. Therefore, clearly specified data privacy practices and agreements always need to be in place. Finally, more work needs to be done to make sure that service providers are receiving the data that they need. This will make the job of service providers easier and allow them to better serve the people who need it most. This will also allow appropriate allocation of finite resources and people power.
And that brings us to the end of our presentation. You can check out HUB at our URL, hub.ucsd.edu, or contact us for further information. We host all different sorts of data sets that we've collected on the topic of homelessness, and we are always looking to collaborate with more partners in the San Diego area. Thank you.
Great, thank you so much for that talk. I want to encourage people to put questions in the chat if you have any, so we can ask them for our speakers. I guess one question, I'll ask you the same one I asked Taylor about this. I'm kind of curious how the planning for this kind of tool went. Did you did you plan it all out and then implement it, or did you implement it in pieces? What was your approach to making this kind of thing work?
Sure, that's a great question. So with the different data instruments, we approached it with like a design thinking framework where we sought to clearly understand the evaluation objectives of our stakeholders, and then ideate a survey based on their existing data collection tools, be it paper or digital, and then refining it such that it made sense in a digital collection pattern, and then talked with current field workers to see if the instrument worked for them, and then ideated until it was a feasible application for field work, and then it was implemented thereafter.
Great, thanks. So it looks like I'm not seeing any questions in the chat besides mine, which is perfectly fine. It's the end of the day, and I think we're ready to end the session. So thank you everyone for coming. Remember that to keep an eye out for the link for the survey that we'll put out to get your feedback on what you experienced today and in the next couple of days on UCGIS week. And I hope you join us tomorrow and Thursday for all of the wonderful sessions we have coming up. And thank you all, and join us on Slack for more discussions there.
I also just wanted to say thanks again for all of our presenters.
Yeah, great job today, guys. It's been a fantastic slate of talks.